The next topic we're going to discuss is the so-called electrical energy and power. In fact, we study that in an electrical circuit. What I have here is a very simple, in fact, the simplest possible electrical circuit, consisting of a battery and a resistor. If you hook up the battery and the resistor together in a self-enclosed loop, then a current will start to flow, okay? From the positive terminal of the battery going through the resistor and going back to the negative terminal of the battery and start over again. Let's say the voltage difference across the two terminals of the battery is epsilon. Okay, we typically use epsilon to denote that. And we can then, from that, we can find the voltage difference across the two ends of the battery. Because, you know, if you go through a whole loop, the total change in potential, the total change in electrical potential should be zero, right? Because just like you start from the second floor, you go up to the third floor, fourth floor, and go back. As you come back to the second floor, what is the total change in your gravitational potential energy? Well, that will be zero. Same deal. Okay, so we start from here, right? Let's say the potential here is zero. We can define this to be zero. We go up to epsilon, okay, which will bring us to that point, and then we have to go down. Let's say the potential difference is V, okay, from here to there. It drops by distance, by an amount V, and that will bring us to this point, which has the same potential at that point, because that's just a conducting wire. Okay, so we have epsilon minus V equals 0. Okay, goes up by epsilon, goes down by V, should add up to 0. So V equals epsilon. Okay, that's something that we keep in mind. Now, that's of course, we assume there is no internal resistance from this battery. Otherwise, it's a slightly different deal, but we're going to study that in the next chapter. Okay, we're interested in just how much energy the battery would have to expend, okay, in order to keep the current flowing. Or more precisely, how much power does it have to expend? Well, let's look at a time interval dt, during which a certain amount of charge went from one terminal, flew through a certain cross-section, okay? I shouldn't say going from here to there, because the same charge doesn't really move quickly from this point to that point. Rather, we install a little cross-sectional area here, and we install a counter here, and we found over this little time interval dt, a certain amount of charge dq passed through that, so that's dq. Okay, so you say an amount of charge dq entered this side of the resistor, the same amount, an equal amount, went out from there. Okay, so effectively speaking, we transported an amount of charge dq from here, from this potential to that potential. Now, here the potential drops, right? The potential drops by an amount V. Okay, if the potential drops by an amount V, and you take this much charge to go through a potential difference of V, okay, dropping by V, what happens to the potential energy of this much charge? Well, that would be, by definition, negative V times dq. Right? Negative V times dq. Negative V because the potential drops by an amount V, so it's negative V. The change in potential is negative V times dq. What is that? That is the change in electrical potential energy of this much charge as it's being transported from here to there. Okay, it loses potential energy, right? Now, when it loses potential energy, what happened to that energy? Okay, we wish to know what happened to that energy. Well, that's quite easy to understand, because as the charges push their way through the resistor, they have to overcome the resistance. In other words, they have to collide with other particles. And as they collide, they will pass their kinetic energy to other particles and start over. Because if that does not happen, okay, if that does not happen, then as a charge goes from here to there, losing potential, electrical potential energy, it's going to pick up kinetic energy. So it's going to go faster as it emerges from the other end, right? We know that doesn't happen. The speed of the electron traveling here and there are the same. It's because, you know, the electron must have passed its energy along by collision as it travels through the resistor. And that will make the lattice ions vibrate faster, okay? Which in turn will increase the temperature of this resistor. So it's easy to understand now why as you turn on an incandescent light bulb, okay, you turn it on, you find the light bulb becomes very hot, right? You don't want to touch the glass surface because it's very hot. It is because the the electrical energy is turned into heat, into thermal energy. So that is the amount of energy, the electrical potential energy lost. It becomes a thermal energy. Okay, so how much work? Okay, how much work is done by the battery meanwhile? Well, the work done by the battery would be equal to the energy expended in thermal form. Okay, and therefore the work done by the battery would be this amount, right? Because the absolute value is the amount of potential energy lost, which is turned into thermal energy, and that energy comes from the work done by the battery because of the conservation of energy. Okay, so it is equal to just V dq. This is the amount of work done by the battery. Okay, and that is in transporting amount of charge dq. So how fast is work being done? I have to take this dw and I have to divide it by what? By dt, right? So dw over dt. That is the power expended by the battery. Power delivered by the battery. Let's see what that is equal to. V dq over dt. Oh, wait a minute. I know what dt is. I know what dq over dt is. That's just the current going through the wire, right? So this is really I times V. Okay. A very simple but important formula. P equals IV. What is that again? That is the power expended by the battery in driving a current through a resistor of voltage of potential difference V across its two ends. Okay, so, and that is also the rate at which thermal energy is being generated on the resistor. So the resistor gets hotter and hotter and hotter, and some of the heat is dissipated through the air. Now, we can also rewrite this from Ohm's law. Okay, from Ohm's law, because V equals IR, so it's I times IR, so I can write this I times IR, or I squared times R. I can also write this by rewriting I as V over R, again by Ohm's law, so it's V over R times V, and that is V squared over R. Okay, all these are equivalent expressions. So this is the electrical energy, actually electrical power delivered by the battery in order to sustain this current. Now, it's interesting for us to check the units. We know that if we didn't do anything wrong, the units should work themselves out. But let's just verify that, okay? This is measured in amps. This is measured in volts. This is measured in watts, right? Electrical, this is just the power. Electrical power, any power, is measured in joule per second. So, is it true that 1 watt is equal to 1 amp times 1 volt? Is that true? This is named after Marie Ampere. This is named after Alexander Volta. This is named after James Watt. As far as I know, these three people have never met. Okay, is it true that 1 watt equals 1 amp times 1 volt? Well, let's see here. Let's check if this is right. We rewrite 1 watt as 1 joule per second, right? Now, as far as amp is concerned, I'm going to rewrite 1 amp in terms of 1 coulomb per second. Okay, that's the definition. And what about volt? What about volt? Well, volt is related to electrical energy and charge, right? It is in fact the unit of potential, electrical potential, which is potential energy divided by what? By charge, right? But electrical potential energy is measured, of course, in joule over what? Charge, which is coulomb. You see here, that cancels, and that cancels. You're left with 1 joule equals 1 joule. So indeed, this is correct. Okay. Now, in 1C, we have already defined several units: coulomb, amp, farad, that sort of thing. And there will be a lot more units to come. Okay. In fact, we define more units than 1A and 1B combined. Every one of them is named after a physicist. So often you encounter a certain formula, you find that it's interesting. Really, it's interesting as an exercise to see if the two sides balance unit-wise. Even though each is named after a different person, it turns out you can always do something like this, and you will check for yourself that the units actually work out. Okay, as an example of this formula at work, let's take a look at a real life example. Suppose I have a 100-watt light bulb. Okay, now you have seen one of those. A 100-watt light bulb. What does that tell you? It tells you that the power going through this light bulb, okay, that's dissipated on this light bulb, when you hook up to the right power supply, is 100 watts. Okay, or more precisely, the time average value of the power is 100 watts. Suppose it's 110 volts. Okay, so this is the U.S. Domestic power outlet is always 110 volts. This is 110 volts. This is 100 watts. Okay, you can find then the current going through a 100-watt light bulb easily. So current going through a 100-watt light bulb would be P over V, which is 100 watts over 110 volts. So it's about 0.9 amps. Okay, that's one thing you can do. And if you can also work out the resistance of the tungsten filament of a 100-watt light bulb, because this is 100 watts, right? This is 110. So R equals what? P over V squared, right? P over V squared, and that equals to 100 watts divided by V, which is 110 volts squared, and whatever that is. That will give you, it's about 1/100th of an ohm. Okay, that will be the resistance of the tungsten filament, and you can calculate that for other, incandescent light bulbs as well. As a matter of fact, if it's a 60-watt or 50-watt light bulb, you find that R is actually smaller because the power is smaller and voltage is the same. Of course, if you put the same light bulb on a different power supply, which says, instead of 110 watts, 110 volts, it says 60 volts or whatever, and then you're not going to produce the same amount of power. Okay, because R is the same, presumably, assuming the temperature doesn't change by much, but V is not the same. Okay, V is smaller, and therefore the power will be smaller. So if you take a light bulb that is designed to operate here in the US with 110 watts, 110 volts as the normal hookup, then you take that light bulb, okay, you hook up to the outlet of another place which has only artificial, let's say 60 volts, then you're not going to get the same amount of power. You get small amount of power. As a result, it's not going to glow as brightly. Okay, but on the other hand, if you take the same light bulb, you go to Asia, okay, except for Japan, you go to Asian countries, and you hook up to a light bulb outlet there, which is 220 volts. Okay, V is 220 volts. Then you can see from this formula here, okay, for the same R, P will be 4 times as much because V is doubled. So it's going to glow very much brighter, but unfortunately that also means that maybe too much current will flow through it. You might fry it. Okay, so that's what happens. Another thing that will come back later, I just want to start mentioning here, is that the power, as you can see here from this formula here, the power dissipated, the electrical power dissipated into thermal form as a current I goes through a resistor R, it goes like I squared times R. Now, this issue becomes important when it comes to transmitting electrical power through power grids. Power plants are usually built in a rural area, and on the other hand, the heaviest consumption of power is usually concentrated in a big city, and there could be many miles of transmission lines between the power plant and the load, which is in the city. And these power transmission lines, even though they're made of copper wires, they're excellent conductors. Because of the very long distance, okay, R could still be large. And that means potentially you could waste a lot of energy, waste a lot of electrical power just transmitting the power through. Okay, so to reduce that, what we can do is we can try to reduce the current. Okay, if the current goes down by a factor of 2, then the power lost goes down by a factor of 4, which is a good thing to do. But of course, on the other hand, we wish to preserve the same amount of power transmitted to the load, to the city, while keeping the power consumption on the transmission wire low. So how does one solve this problem? Okay, how does one preserve the same amount of power transmitted onto the load while keeping the current on transmission line really low? That's something we will discuss when we study a later chapter called AC current. And that will explain why they use very, very high voltage across power transmission lines.